Hi, in this video, we're going to do some exam question walkthroughs on the questions that have come up on the ideal gas equation. So the first thing is, can you recall the ideal gas equation? Before we look at them, any of them specifically, what is the ideal gas equation? Pause the video now and see, can you write it down? Which is a very important piece of information. It's one that I always say to my students, it kind of rhymes and rolls off the tongue. My students don't forget it. We practice it so much, but it's just one of those nice ones. It seems to rhyme a little bit. It's PV equals N or T. PV equals N or T. And you guys should definitely know what that is. If you don't, then you probably shouldn't be doing these questions yet. Go and learn about the ideal gas equation in my other videos. All right, so the first thing we're going to say is that this first little question here came from a short question. As you can see, it's part J, which means it's only worth 6 marks, and you only have about 3 to 4 minutes at most to do this. So you need to be quick about this. All right, when we're looking at something like this, PV, N, or T, we need to know at least 4 of these variables, and then we can calculate the other one. That's the idea. Now, because this is part of a short question, you don't have much time, they won't require any conversions of units in here. So they give you pressure in pascals, they give you temperature in kelvins, and they give you volume in meters cubed. All SI units, we don't need to convert anything, so it should be nice and quick. Now, the thing you're missing from here that you would have on an exam paper, and you don't have it here because you don't have the full exam paper in front of you, is R. R is equal to 8.3. It's the universal gas constant. It always has the same number, so I'm telling you that there now. There should be no problem now for you guys to go ahead and solve this question. Calculate the number of moles in this equation. If you know how to do this, go ahead, pause the video, write this down now. Hopefully you've been able to have a go at that. The way I would approach this question is always to write down what I know first of all from the question. And I would do this like this. I would write down the letters P, V, N, R, and T. You guys should have done something very similar to this always when you're doing a question like this. Then I would get you to pause the video. If you didn't do this something like this already, write it down, pause the video, and write down what each of these is equal to. Okay, so the first thing we know is that the pressure was 1.85 by 10 to the 5 pascals. It's already in pascals, so it's good to go. The next thing is V, volume. It told us that it's 6.5 by 10 to the minus 5. And that's meters cubed. That's SI units, so it's ready to go. N is the question mark. That's what it's asking us to find. Calculate the number of moles. That's what it's asking us to find. So we don't know that yet. That's fine. Or I've already explained to you is 8.3. And T is temperature, and it's 293, and it's already in Kelvin, so it's good to go. So everything is good to go except N. All right, so hopefully you can pause the video and solve for N now. All right, if some of you are struggling with this, you're not sure how to do it, it's very important that you get the next step right. What you need to do is write down the equation PV equals nRT, and what you need to do is rearrange the equation to make N the subject. Now that I've told you that, that may have reminded you, oh yeah, I need to do that. So pause the video, do that now. Okay, so how do we do this? If you're really struggling with this, guys, again, I've done loads of examples of this. You should know how to do it. But we need to think about this equation in terms of numerators and denominators. At the moment, there is no denominators. You cannot see anything. It's not being, nothing is being divided by anything else. But we can make a denominator. So what we do is we go to the variable that we want to be on its own, which is N. We go here. And on this side of the equation, we want N to be the subject, which means we want it to be by itself. So what we want to do is remove the R and the T here. And what we mean by removing is we mean that we've got to do some function to it to take it out of the right-hand side. We do this by making a denominator like this, and we put R in the denominator. That means we've got R divided by R, which is just 1, and anything divided by itself is 1. We also want to remove T, so we're going to put T in the denominator. Now, T over T is 1 as well. Now we've got N times 1 times 1, which is just N. Good. N's by itself now, equals 2. Now, because this is an equals, that means equal. That means both sides are the same. Now, both sides aren't the same if we made a change on the right and not a change on the left. So we also need to do the same on the left, where we make a denominator and put those same 2 things in here. Now, just rewrite the rest of it without the crossed out stuff. So PV divided by RT. That's how you rearrange an equation, guys. That's how you do it properly using the maths and not some trick like, oh, you just bring that from there to there, or you cross over, or some nonsense that you might have learned. This is the proper maths behind what you're doing. Okay, so the next thing to do is solve the equation. Guys, you have to at some stage be able to pause the video and go ahead of me. If you're waiting for me to show this to you, you're not going to learn anything. You have to at some stage take away my support and finish this by yourself. So plug the values in, put it in your calculator. Everybody should be able to do this now. All right, so this is what you should have done. I'm hoping is you should have put in the pressure as 1.85 by 10 to the 5 times by 6.5 by 10 to the minus 5, which is the volume. Put that all over, or which we said was 8.3, and T, which we said was 298. Oh no, 293. Be careful when you're transcribing numbers. Okay, so now I'm ready to put this in my calculator to find N, because N is equal to all of this stuff, this math sum here. Put it in your calculator exactly the way it is there, in brackets. And what you should have got is something like this: 4.939 times 10 to the minus 3 moles. Good. Now you might think you're finished, but there was one other important thing here. It said give your answer correct to one significant figure. So go back over here. Here we have this here by 10 to the minus 3, which is important. That's definitely going to be part of the answer. But we've got more than one significant figure here. The first significant figure is this one. It's a number. It's not a zero. So this is the first sig fig, which means we want to round to this number. So what we need to do is decide, does this stay as a 4 or does it get rounded up to the 5? What's the nearest whole number? Pause the video and see if you can figure that out. Write it down. Okay, so what we should have done is we should have said that this is 4.9, which means that that's closer to 5 than it is to 4. So what we're going to do is we're going to round this to 5. And that's one significant figure. And then we put the ending on here. 5 by 10 to the minus 3 moles. That's your final answer there. Well done. Now you wouldn't lose all the marks for leaving it like this, but you'd lose a couple of them. Most of the marks for doing the sum you would have got up there, but you would definitely lose some of them for not round. When it specifically says round to one significant figure, you'd have lost some of the marks. All right, going to the next bit. Let's look at the next question. All right, so a bit more here. We've got, this is worth 21 marks, 22 marks. So nearly half a question. You've got about 10 minutes here, just under 10. All right, so first of all, it says state Avogadro's law. So again, this is a definition, guys. So Avogadro's law. Now, my students have a system for learning definitions, Avogadro's law, where we do flashcards and very regular retrieval practice quizzes on the definitions. If you're not in my class and you're not getting that, then you need to develop some kind of a system to help you learn the definitions accurately and perfectly, okay? They're not opinions. It's not, oh, I kind of think it's something about this. No, it has to be perfect. It's a fact developed over time that people have proven again and again is true, and we have to know what those definitions are, okay? So we're going to pause the video and hopefully be able to have a go at Avogadro's law. What did Avogadro figure out? Pause the video and do that now. All right, well, what Avogadro figured out is that if you take equal volumes of gases, now what we mean by this is if you take 1 liter of 2 different gases, or 5 liters of 2 different gases, say 5 liters of hydrogen, 5 liters of helium. So equal volumes of different gases. Now, so long as you keep them at the same pressure and temperature, it doesn't matter that they're 2 different gases, they will always have equal amounts of particles in them. So if you have 1 liter of helium, it will have the exact same number of particles as 1 liter of hydrogen and 1 liter of carbon dioxide. So equal volumes of gases contain equal numbers of particles. That's his basic discovery. Now, you must clarify though that this is only true if you keep the temperature and the pressure the same. If you compare carbon dioxide at 100 degrees Celsius to helium at 5 degrees Celsius, then 1 liter of each of them will not contain the same amount of particles because you've let the conditions change. So we must clarify that equal volumes of different gases contain equal numbers of particles if or at the same temperature and pressure. So this is an important part of the definition, because if it's not at the same temperature and pressure, then it's not true anymore. So at the same temperature and pressure. So all of this wording is important. to get the marks in this definition, because definition is not true if you don't include the end bit. All right, so that is that. That was worth 7 marks, guys. So look there, that 7 marks is actually worth more than all of this work that you did up here. So that's why definitions are very important. They're very highly valued on the Leaving Cert Chemistry course. All right, let's look at the next one. I'm going to get you to pause the video and read the text there. Okay, so hopefully you've had a read of it. Have you got any ideas about how you might solve this? Pause the video and have a little discussion in your mind. How would we solve this? Pause the video. Okay, hopefully you're thinking, I could use P via N or T. Now, if you weren't thinking that, I want you to pause the video and say, think, can I use PV equals N or T to solve this? Pause the video and think. You may be coming with a problem. You may be saying, I have everything I need because I know universal gas constant is always 8.3. I'm told the pressure in pascals, I'm told the temperature in Kelvin, and I'm told that I want to find the volume. What I don't know is N. Yes, and I agree, you don't know N, but you do know that it's carbon dioxide, CO2, and you do know that you have 2 kilograms or 2,000 grams of it. So you could find the number of moles, N. Okay, so with that in mind, hopefully some of you may be able to pause the video, write down all the data you know, and solve the whole thing without any more help. Try that now. Please try that now. Okay, if you didn't know this, or you weren't confident about this, or you still need some help, you got stuck somewhere, then help is coming. That's what the videos are for. So the first thing to do is write down the data. What do we know? If you didn't try this, guys, you have to pause the video, do it now. All right, so you should have been writing down what V was, what P was, what T was, what R was, and what N was. Pause the video, do it now if you haven't already. First thing I would say is that V is a question mark. That's what we want to find. That's the unknown here. P, it told us, was 1.01 times 10 to the 5 pascals. T, it told us, was 290 Kelvin. And all of this is nice because we're already in SI units, so this is great. Or equals 8.31. No, I'm going to say 8.3. I think that's what was on the front of the paper on this here, 8.3. And N, well, that's the one we don't know. But we do know how many grams we have. We have grams of CO2, and we want to go to moles of CO2. So pause the video and write that down. Do that conversion for me now. Okay, just in case you weren't sure, we have 2,000 grams of this, with 2 kilograms, 2,000 grams. Now pause the video, figure this out for me. All right, if you're really still struggling, guys, basic conversions, you probably shouldn't be trying these exam questions yet. If you can't do a basic conversion like this, go back to the moles, grams to moles video. Okay, so you've got 2,000 grams of CO2, and we're converting to moles of CO2. So what we want to do is we want to make sure that we cancel out our grams of CO2 and we leave ourselves with moles of CO2. The next thing we want to think about is what's the relationship between grams of CO2 to moles of CO2? Well, for every 1 mole, we have this mass of CO2. So we have 12 from the carbon atom plus 2 times 16 from the oxygen atoms. So now that we know that, I'm going to pause the video and do that sum to find out how many moles. Okay, the answer I get is 45.45. I'm going to round that to 45.5 moles. So back over to N, 45.5. All right, so if you were struggling to work out N, that's okay. You should be able to finish it now though. So write down your PV equals NRT, manipulate it to make V the subject, and then finish this off. Okay, this is what you should have done. PV equals to NRT, and we want V to be the subject. So we need to make a denominator on the left, which takes out P. So P over P makes a 1. That leaves me with V. So 1 times V is V. Good. Now I also then need to make a denominator on the right and put P into it. Rewrite my equation. V equals NRT over P. Like that. Easy P. Right, now what we're going to do is we are going to plug in, the values that we know from up here on the previous line. So N, I said, was 45.5 times by R, which is 8.3, times by T, which is 290 Kelvin. Is that right? 200, yeah, 290 Kelvin. All right. All this is over the pressure, which we said was 1.01 at 10 to the 5. All of this should give me V. Pause the video and work out what V is. All right, so I'm going to go ahead and do it. I'm doing 45.5 times by 8.3 times by 290. All that is over 1.01 times 10 to the 5. Press equals, and I'm getting this answer here, 1.084. So what are my units then? Well, it's a volume, and the SI units for volume are meters cubed. So 1.084 meters cubed. That is my volume of my gas. All right, well done. If you got that, it's great stuff. All right, there is another bit that you could easily forget here, and that's this bit here at the end of the question, another 6 marks. It says, what mass of helium gas would occupy the same volume at the same temperature and pressure? Without me giving you any more clues, I'm going to ask you to pause the video and think about how are you going to do this? How are you going to approach it? Pause the video, do that now. Okay, so hopefully you're thinking, we've got the same temperature and pressure. Now, what did you learn in Avogadro's law? If you weren't thinking about Avogadro's law, then you're probably doing this wrong. So think about Avogadro's law. Pause the video, do that now. Okay, so same temperature and pressure means that what's Avogadro's law? We said equal volumes of different gases. So we have different gases. We had helium gas here, carbon dioxide gas here, but we know it's the same temperature and pressure. And we've got, if we had the same volume, equal volumes, what would that mean about the number of moles? It would mean that they have the same number of moles. So how many moles of carbon dioxide did we have? Well, we worked that out just here, look, 45.5. So if we had 45.5 moles of helium gas is what they're asking us here, what mass would that be? So you guys should definitely be able to solve it from here. Pause the video, try and solve this equation, try and solve this problem now. All right, so if you're still struggling for how you would do this, we need to go from moles of helium to grams of helium. Pause the video, solve the problem. All right, so hopefully you set up a unit analysis where we went from moles of helium and we times by, well, we want to go between moles helium and grams of helium. All right, so we're starting with 45.5 moles of helium because that's how many moles of carbon dioxide we had, and we know it's at the same temperature and pressure, so the volumes are the same, the moles are the same. All right, 45.5 moles of helium. What's the relationship between moles of helium, grams of helium? You should be able to do this. Pause the video, write it down. Again, we learned that for every 1 mole of helium, it would have its molecular mass in grams. Now, helium gas, if you look at the periodic table, has a mass of 4. So 4 grams for every 1 mole. Pause the video, go ahead and finish this. All right, so 45.5. 45.5 times 4 equals 182 grams of helium. So moles of helium cancel with moles of helium, left me with grams of helium, which is what I wanted in my answer. That's why the unit over here is grams of helium. That's the correct answer, 182. Well done. Okay, if you got that right by yourself, that's brilliant. Well done. All right. Next question. Again, we've got another definition. I'm just going to jump straight into it. What is an ideal gas? Again, I'm going to pause the video and write it down. If you find yourself, guys, not being able to answer these definitions, you need to spend more time on them. Okay, you see how critical they are? You can't be just writing off 4 or 5 marks. If you want to get H1s, H2s, these have to be guaranteed marks. Okay. All right. So what is an ideal gas? This is what you should have said. It's a gas which follows all the assumptions of the kinetic gas theory, or actually we'll just say the ideal gas theory. the ideal gas theory under all conditions of temperature and pressure. So that is an ideal gas is one that follows all the assumptions. So remember, we learned 5 assumptions of the ideal gas theory, and it has to follow all of them for all conditions of temperature and pressure. It must also follow the gas laws, so Boyle's law, Charles' law, all those laws as well, which sometimes you'll see that as part of this equation, but sorry, a part of this definition, but I think that this here is fine. Gas, it's a gas which follows, sorry, I should say a gas. It's a gas which follows all the assumptions of the ideal gas theory under all conditions of temperature and pressure. All right, on to the next question. It says, give one reason why real gas like carbon dioxide deviates. This means like disobeys or moves away from, disobeys. So a student who breaks the rules in school, they will say they deviate from the school rules. They do something different from that. So this is what this is saying. Give one reason why a real gas is not an ideal gas, basically. Which one of the assumptions does it break? So real gases. What makes them different? Why are they not ideal? Pause the video, write down one reason. Okay, so the main reasons we discuss here from the rules is that one of the rules of the ideal gas law says that there are no attractive forces between the particles. This is not true. So gases have, we should probably say real gases because that's what we're talking about. Real gases have attractive forces between the particles. Because one of the assumptions of the kinetic gas theory is that there are no attractive forces between the particles. So real gases have attractive forces between the particles. That's one of the reasons, and you only needed one. Another one you could have said, another one of the assumptions is that the size of the particles of a gas is negligible or is minuscule compared to the spaces between the gas particles. Now, what that says is that, for example, I'll show you when this isn't true. For example, if we take a syringe full of gas like this, and we will draw the particles in here. I'm drawing them very tiny, as you see. So these are particles of a gas. Here we can say that the particles are very, very tiny compared to the space between the particles. So this is a low pressure. So under low pressure, this is kind of true, that the particles themselves are tiny compared to the spaces between them. But if we take that same syringe and we put it under high pressure, which means that we take our plunger and we push it in, we squeeze it in. Now we've put it under high pressure. Well, now most of the whole gas, the space, is taken up. So we assume the end is sealed in both cases, so the gas can't leave. Now, most of the space here is actually taken up by the particles themselves, and there's barely any empty space anymore. So under high pressure, that rule isn't true. The particles are not negligible in size relative or compared to the spaces between the particles. So that's the second one that we break under high pressure. That rule that we said about ideal gases really isn't true. So we could say under high pressure, particles are not negligible relative to the spaces between the particles. All right, on to the next one. We're into the calculations now. This is where students usually need most of the help with. It says, assuming ideal gas behavior, how many molecules of carbon dioxide are present in 720 cm cubed of the gas at 10 degrees Celsius and a pressure of 1 × 10⁵ pascals? Give your answer correct to one significant figure. Okay, so what I want you to do is I want you to pause the video. I want you to reread this now. And what I want you to do is I want you to think about how am I going to solve it. Pause the video, do that now. Okay, so what we're looking at here, hopefully you are thinking, I could probably use PV nRT because I have a volume, I have a temperature, I have a pressure, and I have R because I always have R. And I could then find N. So yes, hopefully you were thinking, I could use PV nRT. There are some problems here though, and that there are going to be some conversions. I want you to pause the video and identify what you are going to have to convert. Okay, I'm hoping that what you figured that you would have to convert is the volume, because it's in centimeters cubed, it needs to be in meters cubed, and the temperature because it's in Celsius and it needs to be in Kelvin. We already have it in pascals, so that's fine. All right, so what we're going to do is we're going to pause the video, and for part 3 here, you're going to write down the data. Data is the information from the question, data. Pause the video and do the data. Okay, hoping that you did something for P, something for V, something for N, something for R, and something for T. If you didn't, do that now. Pause the video, do it now. Okay, so first of all, P is, well, that was 1 × 10⁵ pascals, no conversion necessary. Volume is 720 cm cubed. So volume equals 720 cm cubed. And we're not happy with that. What do we need to do? We need to go from cm cubed to meters cubed. We'll do that in a second. N is what we're trying to find, moles, so that's our question mark. R is 8.31. And then T, it said, was 10 degrees C. 10 degrees C. And what we need to do is go from degrees C to Kelvin. All right, so hopefully you guys know how to do them conversions. Pause the video and do them conversions now. All right, so again, I'm trying to give you more and more chances to do this by yourself, not be relying on me. If you're still relying on me for all these things, then we probably are wasting our time doing exam questions. You need to go back and learn how to do them again in the videos, the theory videos where we learn them originally. That's a better place than jumping into exam questions. All right, so let's go ahead and do the conversions for volume first of all. I want to go from cm cubed and I want to convert to meters cubed. So cm cubed, I will cancel there and leave me meters cubed. Right, I know then I started with 720 cm cubed. How do I convert? Pause the video and write in the conversion factor here. Okay, what you should have done is for every 1 meter cubed, there are 1 × 10⁶, or 1 million centimeters cubed. Okay, all right, so go ahead, get that on your calculator, figure out what that is. All right, what you should have done is you should have figured out that this here is, it's 7.2 × 10⁻⁴ meters cubed. All right, let's do this one. Celsius to Kelvin. Pause the video and do that now. Okay, so hopefully what you did here is you took 10 and you added 273. That's all we do to convert to Kelvin. Get 283 Kelvin. Right, ready to go now. We need to do PV equals nRT, but we need to make N the subject. All right, so we're ready to do that. I think we're going to put PV equals N, R, and T. And what I want you to do is pause the video and rearrange, make N the subject. Okay, if you didn't know how to do this, guys, again, I'm getting worried if you didn't know how to do this. You're obviously not listening or watching carefully to what I'm saying when I'm doing it if you're still struggling to do this. Okay, so what we need to do is think about this in terms of numerator and denominator. Well, at the moment, there's no denominator. On the side where you want to isolate one of the variables, in this case, we want to isolate N, we need to make a denominator on that side. And we need to put the things that we want to get rid of into the denominator. We want to get rid of R, so R divided by R is 1. We want to get rid of T. T divided by T is 1. This is N times 1, which is N. N equals then, and then of course what I need to do is, because it's an equals, I also need to do the same on the other side, R over T. Now nothing here can cancel on the left, so that means I'm going to do PV over RT. Now we're going to plug in our values from our data line up here, and we're going to solve for N. Do that now. Okay, so what we should have done here is we should have done P, which was 1 × 10⁵, and times that by V, which is 7.2 × 10⁻⁴. All of this is over 8.31 oh, sorry, 8.3 we're going with here. Oh, we'll go 8.31, that's fine. And we are going with Kelvin 283. Pause the video, stick that in your calculator, see what you get, please. Okay, so what you should have done here is you should have got, let's see what we got. I'm going to do this with you. So 1 by 10 to the 5 times by 7.2 by 10 to the 4, 10 to the minus 4. Making sure that's 10 to the minus 4. All over 8.31 times by 283. All gives you 0.306 equals 0.306, which I'm going to round to 0.031. So 0.0306, sorry, is what I had, and I'm going to round that to 0.031 right now. All right, and this, of course, is moles because I was finding N. So if you got that, well done, guys. If you got it all by yourself, brilliant. If you got it with a little bit of help having to pause it, very good. If you're still listening to me all the time, guys, I'm getting worried because we're on the third one of these now. Okay, which means you need to do more and more practice, find more of these, or go back to the start and do them again. Pause, like blank page, go back to the very start of this video and now try again without my help, because you have to start losing my help. That's the point. All right, the last bit, there is another piece of this question. Be careful. It says how many molecules. We just found out how many moles of carbon dioxide. How many molecules of carbon dioxide are present in this quantity of carbon dioxide? So we have moles and we want to find out how many molecules that is. So what we're going to do is pause the video and do that moles to molecules conversion. Pause the video and do that now. All right, so I'm going to use a unit analysis to do this. I'm going to start with moles and I'm going to convert between moles and molecules. So moles versus molecules. Right, again, pause the video, write down what the conversion here. Well, first of all, we started with this many moles. That's how many moles of CO2 we had. So that's our starter over here, 0.031. Then what's the rule? Well, I know if I have 1 mole of anything, I have Avogadro's number of that thing. So if I have 1 mole of molecules and I have Avogadro's number, I have 6.02 by 10 to the 23 molecules. All right, so go ahead and finish this off before I do. And if you did this by yourself, superb, well done. The answer I'm getting is 1.8662 times 10 to the 22 molecules of CO2. So that there is your final answer. And if you got that, well done. All right, now if you're obviously, you might have got something very slightly different here, 8, 6, 7 something, if the rounding is just a very slight problem. If you had something, if you left this as 0.0306, then this is going to be very slightly different. But this number here should definitely be the same. And this here, 1.8 should definitely be the same. Even 1.86 should probably be the same, but definitely 1.8. If it's close and it's in that region, then you've probably done it right. If it's way off, then you've done something wrong. All right, guys, I hope you found this video helpful. Thanks to all the people who've been liking the videos. It's definitely helping more students who are not in my class, in my school, to find the video. And what I'm being told is that they're helping a lot of people. So if you could keep dropping a like, guys, it would help more people find the videos. I appreciate it. Thank you. We'll see you in the next video.